Okay, just an idea. You don't have to do this. But analogous to what I'm asking my intermediate algebra students to do, they've never seen the special products for a plus b, a squared plus 2ab plus b squared, and a minus b times a plus b, which is a squared minus b squared. I'm sure you've used that in your math classes fairly often. But imagine that you're really familiar with it. If not, wonder what's going on. But in teaching how to use this, because they're not familiar with the idea of substituting something for some other variable. Okay, at least not very familiar. They know how to do it. If they've got an equation, they have to substitute for x to check the equation, although they never do. But when I ask them to understand that this is an instance of this, they need a little bit of help. Okay, I can stand there all day and say, see, this is just like this, and this is just like this, and this is squared, and this is squared. So you could let a equal 4x, and you could let b equal 3y, and then you could substitute that in for a and b up here, and you'd get an answer pretty quickly, more quickly than you would if you wrote out a plus, this times this and use the distributive law. Okay, which they're fairly good at. So it's a shortcut. It's going to be really important when they have to learn to factor a little bit. Well, what do I tell them? First thing I said is this equals a squared plus 2ab plus b squared, as long as a equals 4x and b equals 3y. Okay. Well, that's a little bit of a jump. I probably should have told them what I said here. In this example, this equals a plus b squared, because you can immediately identify this form as being the same form here. And then you can see that if a equals 2x and b equals negative 5y, okay. But I wanted to make them think a little bit, so I did it like this. And some of them got it, and some of them didn't. Then I wrote it out like this, okay? And I tell them, I want you to use all the words that I'm using. I want you to copy my words down exactly when you do the homework, the first few homework problems, because I want you to tell yourself what you're doing at every step instead of just imitating something you're going to forget. Okay? So I tell them for a equals this, for a equal 2x, b equals negative 5y. So this equals this. And maybe you're right because this equals this. Okay, making a little more obscure connection between this and this. For a equals this and this equals this. So now you write down this equals this. This being a plus b squared. This being a squared plus 2ab plus b squared. Then there are details because I want to add, because I see that negative 5y and stuff like that. And you deal through. Now, those aren't details that you've got to worry about. But analogously, when you're doing your homework, I would really advocate that you reinforce what you're doing by writing down the principle that's involved. Okay? And I'll talk about that a little bit when we solve a couple of problems. It reinforces what you're doing rather than just getting the solution. Now, maybe that solution makes it very clear to you what you're doing and in such a way that you're going to retain it all the way through the test. Or you're going to be able to review it very easily and very quickly and prepare for the test. Okay. Now, the tests I've looked at so far, for the most part, look okay. Okay. But I haven't really compared it with what the problem actually asks. I'm just seeing physics content here. It looks like it's fairly well developed. Well, not so well over here, but that's the way I've looked at the problems at this point. That's the way I will look at them a little bit more this evening or tomorrow afternoon. Okay. Not sure about this evening because when we flush the toilet upstairs, it leaks through the light in the bathroom below. And I built all that plumbing 40 years ago. But it's PVC and it's welded. Those welds don't come loose. So I don't know what's going on. So I'm not doing anything with it. The shower and the sink work okay. So it's just purely a problem with the toilet, which makes it easier. Bigger stuff to work with and more accessible. Just got to cut out part of the bathroom ceiling below. I'm probably just going to hire it out just because I don't have time. But for that reason, probably going to be tomorrow afternoon before I get to take a good look at these. Okay, I established that all we got to do is use the toilet and bathroom downstairs, and I use one upstairs. And everything else is going to be fine. My wife was actually okay with that. I got out of the house with only minor bruises, no cuts or scrapes. Okay. I was on short time this morning. Well, that's enough about my personal life. And really, my wife is not that violent. I'm just making a joke out of that. A little bit. But I can handle it. Just never turn your back. All right. So just kind of take a lesson on that. And we're just going to talk about that instead of a quiz. I should give you a quiz on a problem with an elastic collision. But everybody's been so focused on the test that I'm just going to take it for granted that preparation for that's going to be uneven. Also, I'll say at least one person was planning to take the test on Saturday, so I'm allowing them to take it tomorrow. And one person got half the test done. And I'm going to make up another half that's not the same as the half they didn't get done. Let them do that. I think I can get that done tomorrow. If not, it'll be a little bit later. I'm also up against a deadline of Friday's shot. Everybody's got an appointment at UVA. So I got to drive her up there and back, and I won't get much else done that day. Except I'm going to take the test along and grade them. Okay. So just explaining that I've got to hustle a little bit to get all that done. So that's my plan. If anybody wants to take that alternative second half of the test, they would be permitted to do so. Okay, within the next week or so. But that depends on my getting it right, getting something in, which should be fairly easy. Okay. Not that the test will be fairly, it should be fairly easy for me to get something equivalent difficulty with different problems and maybe different topics. Now, what we want to talk about right now, and I'm actually going to give this a sort of a quiz to do it in quick. This is something you should be able to do. Magnets, 50 grams. Now we've got, I can bring this over here. Ooh, put anything magnetic near the magnets. Nope. Okay. Tried to capture my drill. Okay, so again, we have this familiar system. Can't quite get it far enough away from the camera, but there it goes. Okay. Now, estimate its angular velocity. Okay, got it? How long did it take to make a revolution? Okay. And if you don't have a good estimate, I don't care what estimate you use, to try to get one that you think is fairly close. If you think it's doing 100 revolutions per second, well, I'd probably be in the hospital because this stuff would fly off at high speed and it wouldn't be good. Okay. And then magnets are 50 grams. So you can estimate where the magnets are. And tell me how much kinetic energy is in the magnets. At the angular velocity you estimated. And usually, don't use numbers like 7.835 radians per second or 7.329 revolutions per second. Use easy numbers, round in easy numbers so you don't have to get hung up with the numbers. Okay. Now you know that this thing's 60 centimeters long, so these magnets are 30 centimeters from the axis. You can estimate how far these magnets are. I want to know the total kinetic energy in those magnets.
What allowed them to practice.
Okay. Now, okay, at an estimated angular velocity of 0.6 revolutions per second, okay, which comes out to a revolution about every 1.5 seconds. It's a little faster than it was going, but still being an okay estimate.
There was a ripe strawberry there, so I would see it. But per grass alternatives, like we mentioned in that lecture, right? Going back to sectors of careers, the agriculture industry. One that I think there's a defined niche, and I think when we talk about the whole niche concept, it's different than ecological niche, right?
With units, I'm going to say that at 30 centimeters from the axis, the speed is 2 pi times 30 centimeters per revolution times 0.6 revolutions per second. That's the circumference per revolution. That's how far it moves per revolution. Why do we use that? Okay. And that's approximately equal to
anywhere nearby, and it's that kind of, makes you want to settle with your title moving on the road.
120 centimeters per second. Yeah, that's rough. It's kind of using. It's a little high, but that's okay. Now, you could use that. You got 4 magnets. So what's the kinetic energy? Well, it's 1/2 mv squared, which is 1/2 of 0.2 kilograms, because each magnet's 50 grams, 4 magnets is 200 grams, that's 0.2 kilograms, times I would avoid confusion by converting the centimeters per second to meters per second, so you know you're gonna get kilogram meter squared per second squared and get a standard unit for energy. Okay. And that's approximately, that's 1.44, and that's 0.1. So we get approximately 0.14. I could write 0.144, but this is an approximation and it's a little high, so I'm just going to use 0.14. And I think I get 0.14 joules. Okay. Now they're actually eight magnets at 30 centimeters, because this is symmetric. I've got, that's four magnets on one end and four more on the other, right?
We have a hydrostatic, right? So it's super easy to murder that mountain drive. Always like to say, well, that's our operating. If your equipment, the other thing that we have, currently.
So maybe you've got 0.28 joules left. Makes sense? So I'm gonna call this K 30. We'll call this K30 with a circle around it, just notational convenience, indicating that's total kinetic energy of magnets at 30 centimeters, right? Now, we also have
We've also got a 4-acre where you can learn how to go under sidewalks.
30 centimeters of beam at each end. Now,
We'll get stop right here and use that. We have pillar attachment, we got a room. Oh, a brush.
200-gram beam, length 30 centimeters implies you got 6 2/3 gram per centimeter. I don't want to deal with fractions. I'm just going to say, okay, it's ballpark 7 grams per centimeter. We're using an estimate for this. We're just trying to ballpark things anyway. Okay. Now we're going to use some symbols in a minute and we'll get a precise formula for all this.
So, dialogue. Optional buddy discussion board that will share any topics at the top of your head. First, we don't have limited time. We have to narrow it down. So this is only a discussion board and a poll sequence. That's what I use to create our first stream.
Mass of 6 centimeters beams, therefore 42 grams. So that means we really have on each end, well, on both ends together, we've got 8 magnets, that's 400 grams. And we've got 42 grams of beam. Okay.
We'll also look at making speakers into
Got 400 grams of magnets. 40 grams of bean.
We are still working on the plan, the information module, plan for us to do.
I'm not sure this is even going to show up. So I'm going to prop up this into the board. I never know where the camera's focused. K30 total, that's what I'm writing, that indicate the total kinetic energy of a segment at the end is, and you can easily calculate that. Just take this 0.14 kilogram meters per second and change it to 0.44 kilograms per second, up kilograms.
So that is gonna be next week. It's gonna be weather, so if weather is nasty, you can probably, guarantee that we won't be doing it. Otherwise, I'll be prepared to, so if we look at that, yeah, I know we looked at this on Monday, but we got our.
It seems a little high. Why is that high? Got 0.2 kilograms. Now I've got 0.44 kilograms. Oh yeah, I'm multiplying by the square of the 1.5 meters per second. And it's going to be basically 10% more than this. This is going to be about.
All right, so we'll drive.
I'm saying about 0.15 joules. Sorry, about 0.30 joules.
The kid here is that.
0.15 is based on this.
What is.
And that doesn't work. Did I do something wrong up there? Oh yeah, you have the 1/2.
Highlighted. So I can tell you for sure that we're not gonna see.
It's 1/2 MV squared, so it's getting screwed up. That works. Okay.
We do have.
Now, do you understand what I did? The numbers aren't important. The numbers just come right out of the calculations if you just calculate it right. Okay. So the idea is we've got 800 grams of magnet at 30 centimeters with angular velocity of 0.6 revolutions per second. Okay. Which would be about 1.3 radians per second. No, it's not 1.3 radians per second. It's like 3.7 or something like that. Okay. Numbers don't matter. But of course you want to get them right. Procedure matters. So one way or another, you figure out how fast this thing's moving. Now, another way to figure out how fast it's moving, if you understand radians, and until you got to understand radians, you're going to be in more trouble than you want to be in this chapter if you don't. You multiply the angular velocity in radians per second by the radius of the circle, something traveling, and you get the number of units of distance per second. Okay? Because a radian is the angle for which the distance along the arc is equal to the radius. You need to understand that and make that connection. Instead of memorizing a bunch of formulas that you're 50% likely to get backwards, because they're impossible to keep track of. I found them impossible to keep track of. You're probably better at it than I was. But I just found it a pain to keep track of, so I just thought about, well, what's that mean? Oh, no, why do we even have formulas? Okay. Use the formulas, be sure you know how to put them together. Okay, well, now I'm just doing the magnets at the end, but We got the mass of the beam, L, the length of the beam, M, magnets, L, the length of the beam segment that we're going to take into consideration. Okay. In our case, this would be our 200 grams. This would be 60 centimeters. This would be 800 grams. This would be 6 centimeters. What did we do? And omega, in my case, 0.6 revolutions per second, approximately 3.7 radians per second. Okay. When you do the calculations, you're going to want to use radians per second. What did I just do over here? Velocity of the magnets is omega r.
There's areas that I would like you all to think about.
R being half the length of the entire beam. That makes sense? R is 30 centimeters, length of the beam is 60 centimeters, so R is half the length of the beam. I didn't list R as one of the variables up here. Could have. But I'm introducing it here and making note that R equals L over 2. So anytime we want to replace R by L over 2, we can do it.
The realm are kind of pivoting on this one, and I'll tell you what we've kind of done over the past. I inherited
Lift up my mask.
some of this from, of course, what we have to do objective wise, but also from the research that I had. He made us read a book, and he got to shoot for 3 books, and that was for your research module. I think that's too much for of course, it's not.
Okay, let me write that a little bigger.
However, do you have some theory of the research? And when I've been doing past years anyway.
Now, you see this in all the calculations that you made and the reasoning that you used. This was all there. And if you use this, you get exactly the same result for the kinetic energy of the magnets that you got before. Because speed is omega r, whatever you got for omega r. In my case, it was 1.2 meters per second. You had different numbers, but it was omega r. And if we replace V by omega r, this is exactly what the heck we get. Okay? You really want to understand that. Because this mr squared here is the moment of inertia of those magnets. It's not the exact moment of inertia because parts of the magnet are further from the center than other parts. And since we're relying on mr squared, r squared is not linear from one end of the magnet to the other. It's a squared quantity, okay? So we can't say it's like the mass of the magnets was all at the center of the magnets, okay? it's off the center a little bit, but that doesn't matter much. We're going to ignore that for the moment, but there it is for completeness. It's a disclaimer. This is not exact. We have the parallel axis theorem that we'll talk about later. It allows you to take that into account. Now, just got a question, so let's make sure we answer everything. The question was, is that an I? I can't believe somebody can't read my handwriting, but okay. Yes, it is an I. It stands for moment of inertia. Inertia being the key quantity. Do not call this inertia. Inertia and moment of inertia are different things. Inertia is resistance to acceleration. Moment of inertia is something that's related to that, but it's not the same thing. It's actually resistance to angular acceleration. You call it moment of inertia. Okay, drives me nuts when I see people calling that inertia. Not really. I'm already nuts. Seriously, it's just a distinction in terminology. If you don't make the distinction, you open the door for a lot of confusion. Okay. So there's the kinetic energy of your magnets. Okay, where M is the mass of the magnets. Now, I was a little careless with my notation. Where I'm using little m, I should be using capital M mag. Right? So let me replace that. I really wanted to have a little m in this expression, but I'll put it in next. So I'm using M mag here, which is the mass of all the magnets.
So I was going to say that we typically do this search for the
in general, I equals the mr squared. Right here, it's the mr squared, where m is for the magnets, but if it was some other mass there, it would just be a little m. And this is what you're going to see. That I doesn't even look like that. I assume it's B. Okay, so I equals mr squared. For a particle, which is like a point mass, at distance r, from the point or axis of rotation. Okay, well, we have other magnets. So I'm going to say V mag, and I'll put a 30 on here.
A lot of it's kind of more on the biochemical side.
No. I'll call this M total 30, total mass of 30 centimeters equals total mass of the magnets at 30 centimeters. And I should put a 30 on the magnet there, but I'll leave it a little bit sloppy. Plus
chromosome level wild genome provides
that's mass of 6 centimeters of beam. Okay, or mass of I'm not even gonna do it simple. I'm gonna just calculate it. It's the mass of the beam.
This is not due for a while, but I just wanted to go ahead.
Times delta L over L. Delta L is that 6 centimeter length, but now it's just a delta L. Okay, so total kinetic energy at 30 centimeters.
So we're not gonna go super in depth on that feature, right? So I'm not going to try to do something I can't do very well. But I will talk about where apply mathematics. Depends on your niche, right? Depends on your sector of the industry. Like, let's just say,
That's going to be 1/2 your total I at 30 centimeters times omega squared.
make sure you get the right ratio is of oil to gasoline, either in the tank, or, what are the temperature requirements of operating a battery? So it's some idea, there's a lot of different ways to go with that. But we'll work on trying to, again, tease out sort of what the niche is, you guys both understand and apply that to that. The other thing is kind of
So it's just your total mass at 30 times R squared, where again, R equals L over 2.
So if you're in the soil class, you get double the soil chemistry. I usually try to set it up where we're doing there.
So that takes care of the little part of the beam out there at the end, which adds about 10%. 3 centimeter piece of beam at least adds about 10% to the mass of the magnet. Now,
the other side is also how industry fix the plant management, where we can use.
we have 2 magnets at 15 centimeters. So,
Those are required for I'm not going to go on. But this is what we're going to be working on.
okay, so this is I, that subscript is halfway.
Those are all like
It turns out that you have 100 grams of magnet and 15 centimeters, which is 1/4 of what you have at 800 centimeters, okay? Probably should have used something a little different here, but we're just going to say that that's
right.
and this M meg, I'm going to call that M meg 30, just in reference to magnets that were 30 centimeters, okay? We're not actually using the 30 except as a subscript. That just indicates the end of the beam, okay? And instead of R equals L over 2, going to be L over 4 because that's 1/4 the length. Those magnets that are halfway to the end are 1/4 of the length of the beam from the end. Now my notation isn't the greatest here.
Documents that I have on here. Review. Then we've got the midterm. Those along with your
It would be something like this.
You have no excuse for not giving it. Any questions? Or any points of discussion that we call the day before?
So you take 1/2 of this moment of inertia that's halfway, multiply it by omega squared. Not going to go much further with that notation. We're going to cut to the chase a little bit. So
It's any day now. I think we're doing a 10-day forecast between this week and next week. It's likely to roll. Doesn't mean it will, but you could use that as a
okay, this is moment of inertia of the magnets at 30 centimeters. Note moment of inertia of the magnets at the halfway between center and the end. And then I'm going to say the total moment of inertia of the beam. And then the total kinetic energy of the entire rotating system is just one half I total omega squared. Now, why can I multiply omega squared by the total I by 1/2 of the total I? Because I use the same omega here as I used over here, because omega is the same for everything on that beam. So omega just factors out of all of the kinetic energies that I could write here. Okay? So I'd have 1/2 I of this, 1/2 of this I times omega squared, plus 1/2 of this I times omega squared, plus 1/2 of this I times omega squared. Okay? So this is a summation sign. I should have made it a little sharper.
Yeah, with the rain, wind, probably.
Total moment of inertia is just the sum of all your MR squared. I'm a little sloppy with my notation here. There's some things I'd like to improve on it. But this is a general principle.
Also, if you.
I now want to apply this principle to figure out what the moment of inertia of that beam is. You've got the moment of inertia of the magnets with just a little bit of an error. We'll explain later, maybe not even today.
Have a good one.
Here's the beam. Got length L. Got mass capital M uniformly distributed. Okay. We got the axis. It'll be the center for the moment. And I'm going to imagine partitioning. And that should be a word familiar to you from calculus, but maybe not. I break this beam into little segments. Now I've only drawn maybe 20 little segments there. Imagine 2 million. Okay? Or imagine we break it into atoms. Or molecules at least. Okay? So we can break it up as fine as we want to, which means we're going to take a limit as the number of segments approaches infinity, which is how you get the limit of Riemann's sum. I'm going to take this particular segment here. And I'm going to say this is the ith segment. So this distance here is r sub I, distance from the axis to the some sample point within that segment. Doesn't matter where that sample point is, because we're going to shrink the segments down toward the limit of zero. Okay, shrink the lengths of these things down to zero. And the number is going to then, of course, approach infinity. Let's give this thing a length. I'll call the length delta r sub I. Let's go ahead and put r sub I in the arrow. Okay, can you see that? I'll make it bigger. So we're isolating one little segment. There's r sub I. Here's the segment. Some random point within the segment. Here's the axis. And this thing has length delta L. What's the moment of inertia? I just asked if the length of this thing is capital L, the mass of the whole thing is m, and this happens to be a segment of length delta L, then what's the mass of this segment? If delta L was 1/20th of the length, could you tell me what the mass is? Wouldn't it be 1/20th of the total mass? If it's 1/1,000,000th of the total length, wouldn't it be 1/1,000,000th of the total mass? Well, connect that. M sub I is delta L over L is just what fraction of the total mass you have in here, right? That makes sense? Another way of reading that is M over L times delta L. Now, really, I should call it delta L sub I because it's the length of the ith segment. So I'll make that. We might choose to break it into equal segments. We often do, but we're not required to do so. In our cases where we get a more efficient estimate, if that's what we're doing, by using segments of different lengths. We would in this case, but I'm not gonna get into that. Okay, now, how do you read this? What would you call M over L? You got a word you might apply to M over L? I'd call it mass per unit length. Or linear mass density. You've seen that in calculus for sure. Okay, you might want to go back and look at calculation of moments of inertia in centers of mass, because that's a standard topic in calculus. Okay, I'll talk to your instructor and see if he really did cover it. I'd bet a lot of money if he did. Okay. We're going to call that lambda because it's a linear density. It's a density per unit of length. If it was a density per unit of area, we'd call it sigma. If it was density per unit of volume, we'd call it rho. I'll use lambda because it's pretty standard. You got lambda times del L sub I. That's the mass of the ith increment. So what's the moment of inertia of the ith increment? We could call that delta I sub I. Subscript is a lowercase. Moment of inertia is uppercase. And they're different symbols. Just because they're the same letter, capital letter is a different symbol than the lowercase letter. Okay? So don't confuse this I with this I. This I is just the number of this segment. Somewhere between 1 and 48 billion. Whatever number of segments you happen to be using. Well, that's MI times R sub I squared. Well, from there, you're calculating the moment of inertia. No, I'm being a little careless with symbols, the way physicists always are. Okay, I'm making certain assumptions. You know, this is like from 1 to n and so forth. I'm just going to write the sum, indicating the sum of all the moment of inertia contributions of all these segments. Okay. And that's the sum of m sub I r sub I squared. Of course, m sub I is sum of lambda delta L sub I times r sub I squared. Might have been better if I'd have done this earlier. But at this point, I'm going to put this on the x-axis. okay? And a delta L is same thing as a delta X, right? Or actually, I'm gonna put it in polar, I'm gonna put it on a polar axis. I'm gonna call it delta R. A delta L is the same thing as a delta R. In other words, R changes by how much on this increment. Well, actually, I called it delta R sub I here. Then I called it delta L sub I down here, right? So I really should have called it delta R sub I throughout, but the meaning is the same. And what you get is this approaches the integral from 0 to L over 2 R squared dr. Now that's just for this part of the beam. This part of the beam will, of course, have the same moment of inertia. Okay. So what that is lambda R squared, or R cubed over 3 from 0 to L over 2. And you can check the numbers on that. You just substitute L over 2 and 0, and you're going to get lambda L squared over 12. Actually, you're going to get lambda L squared over 24. And that would be just for this half of the beam. So the whole beam would be lambda L squared over 12. Okay. This is just for the right half of the beam. You need to understand how this integral is developed, because that's how you calculate moments of inertia. The text will show you that. This is the easiest one. But we can also do other shapes. Now, if you develop the integrals, if you do a hoop of radius A, mass M, moment inertia is I equals M times A squared, because every point on a hoop is at the same distance. So it's all moving at the same speed, and this is what you get. For a disk, It's not right. Fix that in a minute. Actually, I might be right. Thinking wrong in comparison with the sphere. I can do that integral, it's not difficult. Okay, so you get 1/2 ma squared if you distribute the mass over a disk. So if we got a disk rotating, we know its mass, we know its radius, there we have it. A uniform sphere, and these are all rotating about the center. You'll see other formulas in the text, but you should remember these. And uniform beam, a rod, about center, your I is 1/12 ml squared. Okay. Now that's what you get from this if you double it, because that would be the whole beam, this half and this half. About the end, I equals 1/4 ml squared. Yeah. Okay, I was careless when I wrote this down. This would be lambda L cubed over 24. Of course, you're cubing R. Lambda is mass over length. So if we replace lambda by big M over L, this is what we get. And that's actually what I was thinking when I wrote it down without thinking. Okay.
Can't keep up.
And that's consistent with what I just wrote down here. Now, quickly, rotational kinematics is identical in form to translational kinematics. We've been doing a lot of that. That should all be familiar to you. The new thing is this moment of inertia. This is the chapter. Okay. And the two things that come out of that is kinetic energy is 1/2 I omega squared. Okay. It's the first place where you use I. Also, angular acceleration is, well, let's write it this way. Torque equals I alpha. This is like F equals ma. This is like kinetic energy equals 1/2 mv squared. These are correspondences between the things you're familiar with from the problems you've been doing for linear motion to the quantities you get for angular motion. Also, and this is the subject of the upcoming chapter, you're gonna love this. Generally, we use, your text, I think, uses L for angular momentum. And of course, we don't want angular momentum over here. We want P. Okay. Here we have L equals I omega. Now, omega is angular velocity, V is linear velocity. I is moment of inertia, M is mass. So moment of inertia takes the place of mass in everything that you've been using so far, as far as kinetic energy and Newton's second law and momentum. Arrow there. So these are just the three new quantities you have. Now, I've been asking you to calculate kinetic energies of magnets for some time because of the in connection with lab. Okay, so make sure you put that together in the way that I Hope you already have. This is new and this is new. And of course, this is a vector equation and this is a vector equation. Angular momentum acts really weird. You have to have the right-hand rule and everything's in 3 dimensions. We've already seen that the angular velocity of something rotating in this direction is in this direction. Talked about that last time. Angular momentum would then be in this direction. And if you want to change angular momentum by exerting a torque, which would be maybe in this direction, you got this vector and this vector that produce a new torque, okay? And that gets somewhat complicated, and that's why there's a whole chapter on angular momentum. All right, now I think there are problems that are due today. If you look back at the assignments, but you know, we'll put those off till Monday, but you'll have a good bit of homework on problems due on Monday, okay? Even a few problems from the upcoming chapter, just to get your feedback. You should be well prepared to do the problems in kinematics, angular kinematics. But we do need to stay on schedule to cover everything. And, you know, it's kind of a black hole when I give you a week and a half window to prepare for a test, which I kind of done, because I knew you weren't going to get a lot of homework done. Okay, you got to kind of make up for that, but try to do it gradually. Fair enough? Okay.